The first thing you need to know about floating point numbers is that they are not exact. When working with integers, you become accustomed to the fact that numbers in the computer are dead on accurate. But with floating point numbers, this just isn't so. For example, you should never test for floating point numbers being equal to one another. Instead, you should test for them being within some small value of one another. Looking again at the three parts of a floating point number, the sign, the exponent, and the base, I need to point out some special cases. For example, the denormalized numbers. It's possible to represent numbers too small to be normalized. Once the exponent has reached the minimum possible value, it's not possible to move the bits of the base number any further to the left to represent a number. To do so, the exponent then is set to 0 and the base is not set to 0. In this form then, there is no implied 1 bit placed in front of the number. Another special case is 0. With the exponent set to 0 and the base number set to 0, the value is assumed to be 0. Notice that the sign bit has no effect on this. It's possible to have either a positive or negative 0. With the exponent at its maximum value and the base set to 0, the number is assumed to be infinity. The sign bit again is part of the action. You can have either positive or negative infinity. And there's one more. With the exponent set to all ones and the base number something other than 0, it's a special value called not a number. This is simply not valid. This is the result you get sometimes from performing invalid calculations. Rather than crash, this not a number form shows up. Some special things have to be done before arithmetic can be performed. To add two numbers together, it's necessary that they have the same exponents. If they are not the same, the smaller number must have its exponent adjusted by being shifted to the right. Now this shifting causes one after another of the significant bits to be dropped off, and it's possible, if the numbers are different enough, that the 1 bits will all be lost, which means that the addition will have no effect. Subtraction works the same way. The exponents must be equal, so it has the same problems as addition. With multiplication, the base values are multiplied. The exponents are added together. The resulting base could well result in more digits than can be stored, so some precision can be lost. With division, the exponents are subtracted, and the division of the base values have similar rounding problems to the ones with multiplication. The NASM assembler sets some defaults in the coprocessor for the way it handles floating point numbers. When the reduction in the number of digits is necessary, values are rounded to the nearest number, and the denormalized forms described earlier are supported. But there are some directives you can include in your code to change these defaults. This option will cause the numbers that cannot be represented in normalized form to be converted to 0. DAZ means flush denormalized to 0. This directive instructs the assembler not to flush denormals to 0. The float near directive causes values to be rounded to the nearest value. This is the default setting, or you can set it to round up or to the next smaller number. These up and down roundings are not in terms of absolute numbers. They round up toward positive infinity and down toward negative infinity. Or you can set it so all rounding, positive and negative, is done towards 0. And you can enter the default settings to restore things to their defaults.